everyone, welcome to the course Structure Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today is the 13th lecture. We already started the moment distribution method and then we derived the carryover factor and then stiffness factor when one end of the beam is fixed and the other end of the beam is simply supported. So in this lecture, we are going to derive the carryover factor when both the ends are simply supported. Okay. So this is also the moment distribution method. At the end of the lecture, student can able to understand the concept of moment distribution method and they know how to derive the carryover factor for when both the ends of the beams are simply supported. Okay, so quickly we will go to the derivation. So here the beams having simply supported at the both the ends. So let's draw the beam. Let me change the color. We'll take a different color and also clear this. Yes. So we have a beam which is simply supported at both the ends. Simply supported means one support is hinged support, the another support is a roller support and the span is L. Okay. And then here I am going to apply the clockwise couple which is mu and our reaction force R will act upward direction and here we are going to have the R reaction force in the downward direction. Okay, because here also the anti-clockwise couple will be there. No, it's here the clockwise couple will be there. So in order to counteract that, the reaction force will be acting in a downward direction. So as usual, this is support A and this is support B. I am taking moment at A. Taking moment at support A. And then I am going to equate the clockwise couple and then anti-clockwise couple. So you see the RA multiplied by the length is rotating in an anti-clockwise direction. So RA multiplied by L is rotating in anti-clockwise direction. Then what is rotating in a clockwise direction? The clockwise couple is mu. The clockwise couple is mu. So what is the next step you know? The next step I am going to consider the XX section here. I am going to consider XX section here and then going to calculate the value of Mx. So Mx is equal to, you see only two forces are there. One is the force multiplied by the horizontal distance. There won't be any moment. Force multiplied by the horizontal distance, because in the earlier case at support a fixed support was there, so moment will be there, but in this case it is simply supported. At support A there won't be any moment, so only what is there, this RA is acting in a downward direction multiplied by the linear distance is x. So RA since acting in a downward direction, I am putting minus of R multiplied by x, minus of R multiplied by x. Now I am going to substitute this in the double integration equations. EI into d square y by dx square equal to mx. So EI into d square y by dx square equal to mx is minus of R multiplied by x. So integrating both the sides, I will be getting EI into dy by dx equal to minus of R x square by 2 plus integral constant C1. Integrating once again, it will become EI into y equal to minus R by 2 into x cube by 3 plus C1x plus C2. Let's further simplify and rewrite this equation. EY is equal to EI into y minus of R by 3 multiplied by 2, 6 x cube plus C1x plus C2. So this is the equation 2 and this is our equation 1. So we got two equation. Now what is our job? We need to eliminate the integral constant C1 and C2. For that what I have to do? I need to apply the boundary condition. So boundary condition is x is equal to 0 means the deflection is 0. Why? This is both the ends are simply supported. So let's erase this. Now we have a beam like this. This is our x section. If you put x is equal to 0 at this point, support A, the deflection is 0. Okay, if you substitute that, what we are getting, let's see. So write the equation EI into Y equal to minus of R by 6 into x cube plus C1 of x plus C2. So wherever x is there, we are going to put 0 and also y 0, this 0, second term 0. So we will be getting C2 is equal to 0. Now we need to apply the another boundary condition, that is when x is equal to L, y is equal to 0. That means at support B also the deflection is 0 unless the support settlement is given. So write the equation once again, EI into Y equal to minus of R x cube by 6 plus C1 of x plus C2 already we got, that is 0. Now we are going to do x is equal to L. So EI into y already 0. So this is already 0. So 0 equal to minus of RL cube by 6 plus C1 L. Okay. So C1 L equal to RL cube by 6. C1 is equal to RL cube by 6L. If you cancel it, we will be getting C1 is equal to RL square by 6. So already we got the C2 value, that is 0, and then C1 we got RL square by 6. So we need to write this also. RL is nothing but mu. So let's replace it. So we know already R multiplied by L is nothing but mu. So here what is there? RL square by 6 is there. So I write C1 once again, which is RL square by 6. We put RL is equal to mu. So C1 is equal to mu multiplied by L by 6. So you need to rewrite like this. R into L multiplied by L by 6. Instead of RL, I am going to substitute the value mu, so that it will become mu L by 6. So this is the value of C, and then we substitute the C value in the slope equation. Right. Substitute the value C1 in slope equation. Okay. So write the equation. This is EI into dy by dx minus of R into x square by 2 plus C1. So C1 value we got here is plus mu L by 6. Okay. So further we are going to simply simplifying this equation, that is rewrite the equation once again in the new page, which is EI into dy by dx equal to minus of R x square by 2 plus C1 value mu L by 6. I am going to put R is equal to mu by L in this equation. So equal to minus of mu by L, okay, into x square by 2 plus mu L by 6. Now I am going to put x is equal to L in the above equation because this is our beam. If you put x is equal to L, then it will be a support B. We can substitute x is equal to 0 also because at support A also simply supported, we will be getting the theta A value. Okay. So in this case, I am substituting the value of x is equal to L. So if you substitute it, what is happening? Let's see. EI into, instead of dy by dx, I can put theta B because it's a slope at, we are going to find out the slope at the support B, equal to minus of mu by L into, instead of x square, L square by 2 plus mu L by 6. Go to the new page. So we have minus of mu L by 2 plus mu L by 6. Let's multiply the 3 in numerator. So it will become 3 times of mu L by 6. Okay. Plus mu L by 6. So I will be getting minus of 2 times of mu L by 6. If you cancel this, you will be getting 3 times minus of mu L by 3. This is nothing but EI into theta B. Okay. Now, what is the theta B then? Theta B is equal to minus of mu L by 3 times of EI. Then what is mu? Mu is equal to 3 EI by L into theta B. So we got the applied moment. Now we will write the stiffness factor also. Stiffness factor. Stiffness factor is what? Stiffness means the force required to produce the unit displacement or the moment required to produce the unit displacement. So the moment required is nothing but 3 by L. So we need to substitute theta B is equal to 1 because it's a 1 unit rotation. So if you substitute it, you will be getting mu is equal to 3 by L. We will be getting mu is equal to 3 by L. So in this lecture, we have seen how to derive the carryover factor and the stiffness factor when one end is fixed and other end is free, and when both the ends are simply supported, at the time what is the stiffness and carryover factor. So I will summarize in this lecture. We have seen the carryover factor for both the ends are simply supported, and also we have discussed the stiffness factor for the above case. So in next lecture, we are going to take the numerical problem and we are going to solve the numerical problems by a moment distribution method by using the help of stiffness factor and then carryover factor. So thanks for watching this lecture. Thank you.